So this chapter is on pure liquids and solids. We've already studied gases, and the last chapter, 13, is on solutions. And I'll focus mostly on solids. There's a lot to say about liquids, and we'll focus on that. And as an introduction, if you remember back to the gases chapter, when we talked about ideal gases and real gases, molecules and atoms that are behaving ideally in the gas phase will slide right past each other without any type of intermolecular force. That's forces between molecules. And so you can lower the temperature of an ideal gas and it continues to stay as a gas. But because real gas molecules have interactions, intermolecular interactions, they will condense at some point. So we have liquids and solids as a result of that. So then on this next slide, we have listed the three different types of intermolecular forces that are most important: London dispersion forces, dipole-dipole forces, and hydrogen bonding forces. And let's see. We'll start with the London. So there are three names for this force. One's called the London force. Then van der Waals force is also sometimes referred to. And van der Waals studied these types of interactions between non-polar species as well as London. So he gets credit as well. Or you put it all together and you say the London dispersion force. All right, anyway, so you have a simple idea here, simple model. This atom has 2 protons and 2 neutrons and 2 electrons, so that's going to be helium-4. So helium-4 is non-polar. All atoms are by themselves. And you can think about this cloud of electrons that surround the nucleus. And the idea with the London force is that at any moment in time, the electrons might tend to aggregate on one side. In other words, it's kind of a vibration where the electron cloud moves back and forth relative to the position of the nucleus. So there's some motion here. And in an instant, you get this delta negative, partial negative charge here. It's very small. And then a partial or delta positive on this side. So partial negative, partial positive. And that will induce a negative and positive in the one that it's sitting next to. And similarly here, negative, positive. Sitting next to would be in the case of the solid, but this happens in liquids as well. All right, so there's that small interaction. Its London forces are considered to be the weakest of the three. And we can look at boiling point trends as an indicator of the strength of the intermolecular interaction. And if an atom or molecule behaves ideally, there are no intermolecular forces and it'll be a gas at any temperature. The existence of solids and liquids is due to intermolecular interactions. Boiling point trends illustrate the effect. I just said all that. Okay, so we started with helium, then we can go down the group, neon, argon, krypton, and look at the boiling points in degrees Kelvin here instead of C. So helium goes from liquid to vapor at 4 degrees Kelvin. Neon goes from liquid to vapor at 27, argon 87, krypton 121. And that correlates with an increasing number of electrons. So in other words, when the atom is larger, then you've got a bigger electron cloud. And then that tendency for that cloud to move back and forth relative to the nucleus is the same, but the effect is larger because there's so many more electrons involved. So that interaction between them becomes more polar going down the group. All right, not only do atoms have this London force, but molecules that are nonpolar do as well. And here's some examples of some hydrocarbon molecules. You can see here, blow this up a little bit. These are different depictions of the structures. Excuse me, methane is CH4. There's the Lewis structure for it. And then this is this Vesper model, Vesper shape. You have black carbon in the middle, and then the white circles represent hydrogen, and this is supposed to look like it's 109.5 degrees. In the case of ethane, you got 2 carbons, eth means 2, meth means 1, prop 3, bute 4, pent 5. ane tells you there's no double or triple bonds. Okay, so then here is the ball and stick model for ethane, and you can see it's depicting that it's tetrahedral as well. So this is sp3 hybridization here. Propane, all examples here, it's all sp3 hybridization because there's no double or triple bonds. And they're just getting larger, and you can see that there's like this zigzag arrangement that reflects that sp3 hybridization. So they get larger and larger, and the interaction between them gets stronger and stronger. So if you have, from the Lewis structure, maybe it's easier to see, but if you have a if you have a CH, actually I think the dipole is pointing this way, dipole, then it'll be opposed by another dipole in the opposite direction. And remember, these guys are in the plane. It's hard to show you this without waving my arms around. But if this is carbon, and let's say you've got 2 of those bonds in the plane, and I believe carbon's slightly higher than hydrogen. So you've got the electronegativity is greater in carbon, I think. So you get these 2 dipoles that are, this is for the 2 bonds in the plane, and they're pointing overall in this direction. Excuse me. Now if you take the other ones that are out of the plane, maybe one of them's here and the other one's here, those 2 similarly would have dipoles pointing this way and this way, and so they're, undo that. So there's an overall dipole moment pointing that way, and so the red and the green dipoles are going to cancel each other, and the molecule is nonpolar. They're all that way. They're all 5 of these that you see are nonpolar molecules for that reason. So there's dipoles within the molecule, but overall they cancel out. So then if you have bigger and bigger alkane molecules, ane, no double or triple bonds, you can, and there's another representation. Actually, I think I've got it on the next slide. Let me check. Okay. I think I had that in a different chapter. So there is another way to do this, and you just kind of draw the backbone framework, just the carbon framework. So this symbol means 1, 2, 3, 4, 5 carbons, which is going to be the pentane. So this is a different way to symbolize it. But if the molecules get bigger and bigger, then you have them maybe looking like this. And due to the London force, the next molecule will be attracted to the first. The second one will be attracted to the first one. And so you think of that, this molecule is nonpolar, but there's a London force, just kind of movement of the electrons with respect to the nucleus, causes kind of a slight displacement. And hence a small charge. And then the next one kind of lines up with it. Like that. And then you get the next one. And that's going to line up like that. So you've got this situation where these London forces are getting larger and larger because the size of this electron cloud is getting bigger. And then the interaction between them is getting stronger as the chain length increases. And they tend to stick together. So if you hear the expression that, nonpolar molecules will stay together relative to breaking up and maybe interacting with water. Water has its own type of interactions called hydrogen bonding interactions. And so to break all this up and start bonding with water molecules, energetically, it's not so favorable. So they're more stable like this. Water molecules are more stable when they're together as well. So you have that expression, like dissolves like. And anyway, that's more of the next chapter. Excuse me. So with regard to just kind of proof that this is what's happening, no, I don't. You can look at this graph here. And this is the boiling point increasing with the size. Now these are these same hydrocarbon molecules, but this is a different type of model for them. So you've got these are called space filling models. So we just saw pentane. Pentane was 1, 2, 3, 4, 5. And maybe you can see it. The black is the carbon. 1, 2, 3, 4, 5. Something. I don't think I did that quite right. 1, 2, 3, 4. Oh, I did 6. Hold on. Like that. And then the white here, these are the hydrogens. Okay. So it's similar. Organic chemists really like these space filling models. They're a little bit more realistic, I guess. In any event, what we're looking at here is that as the number of carbons increases in these long chains, the boiling point increases as well, which means that the London forces are increasing. So when the boiling point is going up, it's due to the London forces that are increasing due to the size. All right, that was the first one. The second one is called Dipole-Dipole Interaction. Excuse me, and this has to do with two polar molecules that are interacting. So they have permanent dipoles as opposed to like a transitory dipole for London forces. And this is dimethyl. So here you have an oxygen connected to two methyl groups. The methyl groups are sp3 hybrids, although I'm not drawing it very well. And then the oxygen also has 4 groups of electrons, so it's sp3 hybridized as well. And you can see that there would be a dipole moment here. So you got a dipole on that carbon-oxygen bond, a similar one here, and then they're going to add together to make, it's supposed to be a straight line, to make a permanent dipole molecule moment for the molecule. So in the end, you got this dipole lining up with this dipole, and that's a pretty strong force relative to London. Okay, and we can look at another example of interaction between dipoles. So the chlorine is more electronegative. It's got that for a dipole moment. This one as well, and that's how the HCl molecules interact if it's pure HCl liquid. The figure on the right got a water dipole moment actually. And then this in the middle is dichloromethane, and the chlorines are more electronegative than the hydrogens, so you get a net dipole pointing that way. So what if you mix dichloromethane with water? Would it dissolve? Would dichloromethane dissolve in water? The answer would be yes, because the dipole interactions, the net dipoles are going to line up in that manner. So you see the effect of polarity again. All right, so here is a graph that shows a comparison between polar and nonpolar molecules. And I like to maybe draw a line right here. So you have polar molecules on the left, nonpolar on the right. Let's look at the right-hand side first. So silane is silicon is right below carbon in the periodic table, and so is germanium. So you have carbon, silicon, germanium. So this is just like methane. This is just like methane. I mean, they have the same shape, everything, the tetrahedral geometry. The difference here is that the electron cloud has 18 electrons, and with germanium it's 36. So there's a huge difference there, and it's shown in the boiling point. So they're nonpolar, and this is just the size of the electron cloud is increasing. Bromine is in a little bit different category there, but if you just look at the number of electrons, 70, so you see the trend that is the number of electrons increase for nonpolar systems, the boiling point increases. So this is just due to the London effect. Now over here, if you have molecules that are polar, so you have in the periodic table, you have nitrogen, phosphorus, and arsenic. So they all have similar geometries. And this molecule, phosphine, has the same number of electrons as silane, but one's polar and one's not. So look at the difference in the boiling points here, 161 and 185. The difference in the boiling point is due to the fact that it's polar, and there's dipole-dipole interactions. Similarly, with arsenic compounds versus germanium, same number of electrons, non-polar boiling point 183, polar boiling point 211. The difference is due to the polarity in this compound. And same effect here with the halogens, 70, and a huge difference in boiling point due to the fact that ICL is polar and bromine is not. Right, the third force is called hydrogen bonding, and this is the strongest of the three forces. It's about 10% of the strength of the covalent bond, with the other two being less than that. And I think London force is about 1% of the covalent bond. So here's the rule. Hydrogen bonding occurs only between hydrogen and either nitrogen or oxygen or fluorine. So the periodic table, as you know, you got carbon, nitrogen, oxygen, fluorine in period 2. And so it's only happening between hydrogen and one of these three. You don't see it with any other elements. And the hydrogen on one molecule is attracted to the lone pair on the other molecule, which contains nitrogen, oxygen, or fluorine. So you can have, let's see, something simple here. Something with maybe nitrogen. So if you had ammonia, tetrahedral geometry, and then you have another one sitting next to it. You have the hydrogen on one being attracted to the lone pair on the other. So this lone pair right here is part of the hydrogen bond. So the hydrogen bond extends over 3 atoms. You have, in this case, nitrogen, hydrogen, and nitrogen. It's pretty much a linear interaction between them. If it's off angle a little bit, it's not as strong. And most of the time we depict it that way. So you have in one picture of it, you'd say that the lone pair is on the left-hand side. And then, let me draw it again. Oops, black. Nitrogen, hydrogen, hydrogen. So the lone pair becomes a bond, and then nitrogen gets the lone pair. Oops, that one is lone pair. Have I got all the atoms there? Yes, I do. Okay, So do you see what's happening? In one instant, the lone pair is on this side, and you have the bond, and then in the second instant, the bond's over here, and the lone pair is over there. So you can think of these as kind of a resonance. That situation kind of oscillates back and forth. Or you could think of it as being delocalized. That's the molecular orbital theory. So it's really just one big bonding situation where they're equal on both sides. With dots. Probably a line going through the atoms wasn't the best way to do that. But anyway, it can be delocalized. All right, so that's a pretty strong interaction. And here you see water molecules, oxygen, hydrogen, oxygen. Here's HF, fluorine, hydrogen, fluorine. Here's the ammonia I was just referring to. Here's ammonia and water, so nitrogen, hydrogen, oxygen. And here you have oxygen, hydrogen, nitrogen. All right, and then here's a good, interesting question. Explain the following. Ethanol has a boiling point of 78, and water has a boiling point of 100. Why would that be? And look at it a little bit first. Look at these models. And on the left-hand side, you have water. So let me pick this one here. And you have the oxygen in red, the hydrogens are in white. So you can see one OH bond, second OH bond for water. And then the lone pair on the oxygen here is attracted to the hydrogen on the other one. So this is a hydrogen bond. The lone pair on the oxygen here is attracted to the hydrogen here. So that's a hydrogen bond. So there are 4 interactions there in liquid water. And each one of these, if you look, has 2 hydrogen bonds and 2 covalent bonds. So the point here is that oxygen can have 4 groups of electrons. Now over here, you've got, let me restate that. There's 4 hydrogen bonds associated with 1 oxygen. So this hydrogen is hydrogen bonded. This hydrogen, you don't see it, but it's hydrogen bonded. Probably this is a better one here. So this one is hydrogen bonded, that one's hydrogen bonded, and then the lone pairs are hydrogen bonded. So water can have 4 hydrogen bonds. And then ethanol, the formula for ethanol is CH3CH2OH. And the structure of it, you got the methyl group on the end, that's the CH3, then the CH2 here, and you got some geometry to deal with because you got, they're all sp3 hybridized, so you got a bend there, and that's the oxygen with the lone pairs, and then the hydrogen. So this right here is ethanol. So there are 3 ethanol hydrogen bonds, right, to this oxygen that is contained within this ethanol. So there's 4 ethanol molecules, but there's only 3 hydrogen bonds. And you look at this one to see that. So there's 3 hydrogen bonds. Is there a hydrogen bond between hydrogen, oxygen, and carbon? And the answer is no. You can only have hydrogen bonds between hydrogen and either oxygen, nitrogen, or fluorine. So you're not going to see this as being hydrogen bond. So what is the difference then? Why are the boiling points different? There are 4 hydrogen bonds per oxygen in this molecule, and there are 3 hydrogen bonds per oxygen in this molecule. So this one you have to heat up higher to get it to vaporize. That's a really good example there. All right, in DNA, hydrogen bonding is responsible for the structure. And you have your base pairs, thymine and adenine, cytosine and guanine. And you have hydrogen bonding between them, oxygen, hydrogen, nitrogen, nitrogen, hydrogen, nitrogen, nitrogen, hydrogen, oxygen, like that. So they're all candidates for hydrogen bonds. And of course, in the CG, there's 3 hydrogen bonds, TA or AT. There's 2. Doesn't matter here. You can see the strand and some detail here on the bottom. And so you have 2 hydrogen bonds, 3 hydrogen bonds, 2. So that's how the 2 strands are held together, and then there's this twist that happens as well. I'm sure you've studied that in some detail already, but that's a very interesting example. All right, then that's enough on the types of intermolecular interactions. So now this section of the chapter is on vapor pressure, and we can look at the barbecue tank, the propane gas tank attached to your barbecue as a way to illustrate what happens with vapor pressure. And you have the liquid, you can see here, with in contact with the gas phase above it. And you have propane. So propane is 3 carbons, 1, 2, 3. sp3 hybridized all the way around. Excuse me, nonpolar, and I don't know what its boiling point is, but it's pretty low. So you have equilibrium, and equilibrium means that, excuse me, equilibrium means that molecules that have enough energy right at the surface of the liquid can escape and become vapor. At the same time, the vapor molecules can be attracted to the liquid, lose some of its kinetic energy, and come back into the liquid. So you can have back and forth, and if you kind of took a screenshot of it at one point in time, you could count the number of molecules in the liquid versus the number of molecules in the vapor, and the numbers will be constant in time, even though there's this back and forth equilibrium. So you can measure the pressure above the liquid, and that is referred to as vapor pressure. It is a number, a certain number of torr atmospheres, and if you heat it up, then the vapor pressure increases as well. Okay, I had to get a cough drop there. So this slide shows the relationship between the speed that the molecules are traveling and the number of molecules that have a particular speed. So what we find here is that there's a distribution of speeds, distribution of velocities or speeds, and you find that most of the molecules at a certain temperature are traveling with some speed, some velocity. Increase the temperature, most of the molecules are traveling at a higher velocity or speed. Increase the temperature again, and you get them going faster. So we know that that happens. That's pretty much common sense. Also, the distribution kind of broadens, meaning more molecules are moving. So in other words, the area under the curve here stretches out into higher and higher speeds versus the area under the curve here. Should be the same area, but in this case you got more molecules moving at higher speeds. All right, so that's that graph, and I brought that up because it's related to this graph. And again, we're talking about vapor pressure. So the vapor pressure above the liquid versus temperature, you might think that it's a linear relationship. As you increase the temperature, the vapor pressure goes up, but in fact it is a exponentially increasing function instead of linear. So I'm not going to worry about that detail right now. There's an equation called the Clausius-Clapeyron equation that sometimes I present with this topic, but we'll skip that. And the thing to focus on here instead is that boiling occurs when the vapor pressure equals the atmospheric pressure. So if you have a liquid in a container and you start heating it, you know that you see bubbles inside the liquid, right? These are not air bubbles. These would be water vapor bubbles, okay? And they tend to have more and more motion as the temperature goes up, and then eventually they're going to be forced out of the liquid into the vapor phase. So, you know, when does boiling occur? When is there so much bubbles here that the whole thing just completely vaporizes? And you've got a force of the molecule trying to get out, and then you've got the atmospheric pressure keeping it in the liquid phase. And so it's a balance between those two. And so when does it all finally transition? And the answer is when these two forces are equal, and just slightly above that, and the whole thing goes into vapor phase. So that all happens at the boiling point. And then if you look at water, you start heating it up, the vapor pressure is going to be going up, more molecules are in the vapor phase. Finally, it hits the 100-degree mark. This is temperature right here. Hits 100 degrees C, and then it completely vaporizes. Ethanol, on the other hand, the blue one, same thing. There's an exponential increase of vapor pressure with temperature. It gets up to its boiling point of 78.3, and the whole thing just transitions into vapor. Diethyl ether similarly has a boiling point of 34.6. So why would this be? This is an interesting graph. Water boils at 100 degrees because of the 4 hydrogen bonds. Ethanol boils at 78.3 because of the 3 hydrogen bonds. And diethyl ether doesn't have hydrogen bonds because it's just oxygen and carbon and hydrogen. No nitrogen, oxygen, or fluorine. So the molecules are polar. There was a slide on that before. And so the dipole interaction is much weaker, takes less energy to get it to go into the boiling point versus those that are hydrogen bonded. I love that graph. Okay, so then interesting effect here with H2O. And remember that H2O in the gas phase is sp3 hybridized, but you get these lone pair electrons that are basically pushing down, making the bond angle smaller. So you have 104.5 degrees as that bond angle in the gas phase. So what happens when you start to cool it down? Actually, we're looking at liquid. We start with liquid. And you get this approximate geometry as well, even though you are getting these hydrogen bonds occurring. But just like regular materials, as you cool down a liquid, the density is increasing, meaning that the molecules are just getting closer together, right? And so water behaves like other materials until it gets to about 4 degrees C. There, you know, just as you would expect, the density is increasing, but at 4 degrees C, water is considered to have its highest density. Now, if you keep going below 4 degrees C, the hydrogen bonds here get stronger and stronger, and there's no difference between this, you know, this is lone pair attracted to hydrogen, attracted to oxygen, right? Lone pair, hydrogen, oxygen. So oxygen, hydrogen, hydrogen. And there's 4 hydrogen bonds that become equivalent. So when they're equivalent, then it's going to become pure tetrahedral. This bond angle will open up to 109.5, and all 4 of these covalent bonds and hydrogen bonds, all 4 of them will assume 109.5 pure tetrahedral geometry. So there's more space then between the bonds, so it opens up, and that's going to decrease the density. So when you cool it down for water, all of a sudden the trend reverses. Instead of the density increasing, it starts to decrease. And so the ice cubes start to form, and they float. They float to the top. So as hydrogen bonds are formed, the system expands due to the space between the network of tetrahedral hydrogen bonds. Density decreases as the temperature is lowered and becomes constant at 0 degrees C when the solid's formed, and then the ice cubes float. All right, I love that example. And then this is the last slide. This is just information. It's informative, but yet important, and we'll talk about it again for the next chapter. So here you're looking at water, and you got solid, liquid, and vapor. There are different temperatures and pressures associated with the material being in the solid phase. A temperature range and a pressure range associated with H2O molecules in the liquid, and similarly for the vapor. And then, so in other words, let's say it was some different molecule besides water. We know a lot about water, but, well, we can use water. So if we had water, let's say at 130 degrees, and the pressure was maybe 740, something like that, you could go to a phase diagram and say, okay, we know it's going to be in the vapor phase. If you have it at the same temperature, but now your pressure is higher, then it's going to be in the liquid phase. So you can go to the phase diagram and see what phase it's going to be in. And then there are these lines that differentiate between solid and liquid and the other phases as well. And those would be considered as equilibrium lines or curves. And the transition between solid and liquid can occur at any pressure temperature combination that makes it fall on that curve. So it can be, minus 10 and 800, or it could be, 0 and 760, but any points that are actually on the curve will be associated with the equilibrium between solid and liquid, and you can get the transition to occur. So if you're going from left to right, let's say you start with a solid here, you start to increase the temperature, it'll go into the vapor phase right here. That's where the phase transition takes place. And then now you got liquid, and you keep going, keep heating it up until you get over here. So if you increase the temperature, you get this effect. If you increase the pressure, you have an interesting effect right in this region between solid and liquid. And so let's say the system has got these conditions, temperature and pressure. And if you start to increase the pressure on the solid, it will transform into the liquid. And that is unique for water. In most cases, when you put pressure on a liquid, it's going to become a solid. So in other cases, all other molecules besides water, this has a positive slope. The solid liquid curve is positive as opposed to the negative slope for the water. So normally, you can start with a liquid, increase the pressure, and it'll become solid. But in the case of water, you start with a solid, increase the pressure, and it'll become liquid. So that's kind of an interesting effect for water, the only molecule that does that. And can think of the example of ice skating. So you're ice skating on solid H2O. You put pressure from your weight on the blade of your skates, and it'll cause transition. So you'll see on the ice tracks that are liquid sitting on top of that solid, and as you skate away, you look back and you can see your tracks due to that transition. Anyway, there's other parts to this graph. You have the critical point, and you can heat either a gas or a liquid, and it's going to transition, and finally you get to this point, and that transition is no longer possible. Instead, you get a fluid at that point called supercritical fluid, and it has properties that it cannot be compressed to the point of making a liquid. So all molecules and elements have supercritical temperature and pressure conditions, and they're referred to as the critical point. There's critical pressure, volume, and temperature, actually. And you probably should Google this. I'm not going to talk about it, but look up CO2 supercritical fluid and look for some YouTube videos where you see the transition. It's so interesting to look at it. You get the gas suddenly becoming this fluid, and there's big movement of the molecules, and they're reflecting light, and they become opalescent, and it's just really interesting to look at. But we won't do that here. Anyway, the last point, I guess, on this graph is that every system has a triple point, and this is going to be the temperature and pressure conditions at which solid, liquid, and vapor all occur at the same time. So there's a triple point, critical point, boiling point, fusion point, and they're all on this phase diagram. So these phase diagrams are very important if you want to study materials. All right, that is the end of the material for this chapter.